Hi, hello everybody. So this is the video dealing with section 1.7, combinations and composition of functions. So this topic will have two videos, and we've divided into two parts. This is the first part, part one, the algebra of functions. Um, so in dealing with the algebra of functions is very similar to dealing with the algebra of regular integers and real numbers. We can perform the same operations of addition, subtraction, multiplication, and division that we do on numbers, and we can do the same dealing with functions. Now, this is extremely easy. I have here a summary where it says the algebra of functions, sum, difference, product, and quotient functions. Seems kind of complicated, especially because you're dealing with domains, but we really don't need the domain right now. All that we are interested in doing is these four operations: the sum, the difference, the product, and the quotient. And we do them, as you can see here, for example, for the sum, the function f plus the function g is just the sum of the two functions. The f minus the g function is just the difference of the two functions, and the same goes for the product and the quotient. Now, in doing these operations, what we are interested in is if the two functions have like terms, then they have to be combined and they have to be multiplied and divided, if possible. Sometimes it's not going to be possible, and I'll have an example for you to see. But in some cases, especially the ones that I'm going to show you here, it is possible to combine them. So here's one case. We'll see the first example. I'm giving you here functions that are relatable. For example, f is 2x and g is x minus 1. And we'll find all of the four combinations of addition, subtraction, multiplication, and division for you to see how that works. So if f of x is 2x and g of x is x minus 1, so here is the addition, subtraction, multiplication, and division. Right? So we write the function f of x, which is 2x. We write g of x. We normally have parentheses, even though this is addition, just in case the function begins with a minus. And now I have to add the 2x and the x minus 1. Now, obviously, 2x and x are like terms, so we combine them into 3x minus 1. So the combination of f plus g is 3x minus 1. The same goes for subtraction, right? So again, we write the f of x minus, which is the operation, and here's the parentheses, and here's the g function. So now I have 2x minus x and minus a minus 1, which is a positive one. So the combination of f minus g is x plus 1. Same thing goes for multiplication and division. So here's multiplication, right? F of x times g of x. So here's f and here's g. And I would just multiply the two. So 2x times x, 2x squared, 2x times negative 1 minus 2x. So this is the combination f times g. And here's the final combination, f divided by g. All right, so f of x as your numerator, g of x as your denominator, and there's nothing I can simplify, and I stop there. Now, notice that there's nothing special about f plus g. I could have combined the two this way. For example, function g plus function h, function g plus function f, function g over function f, and so on and so forth, right? Nothing says that I have to have f first, all right? So we can combine them in any way we want to. So for example, if I wanted to combine g over f, I would obviously have the g function first. So g, and then f of x, which is 2x, over 2x. And that would be the combination, okay? Now, obviously, in this case, notice here that we are restricting that this domain cannot have x value being a positive 1, because if it is, then I have division by 0. In this case, the function after the combination, x cannot be 0, right? Because if it is 0, then I have 2 times 0, 0. I cannot have division by 0. So sometimes this is what they were saying before, that the domain changes a little bit depending on what combination you have. But it's only going to happen with the quotient. All right. So this is the first example I wanted to show you. We'll do one more. This is in the textbook, so you can always take a look at it later. Let's take a look at one example, which is also taken from the book, as you can see here, example 2. So afterwards, after watching the video, you can go for more of the specific details inside the book. So I'm giving you again two functions that are relatable, meaning that they're both polynomials. One is of degree 2, the other is of degree 1, that we can perform these combinations, and there's going to be some simplification along the way. So f plus g, let's do the first one, f plus g. So f plus g, all right? So I write the f function, I write the g function, and then I just add them, right? So the x squared component is unique. There is no like term to that. I have 2x plus x, and I have the minus 1 plus the minus 2, which is minus 3. Right? So this is the addition. And if you want, you can write it this way. F plus g of x, x squared, 3x minus 3. Now, let's do the second one. F minus g. Now, in this case, you have to be careful because of the minus. I have to put the second function in parentheses, otherwise we're going to have a problem. So here's the f first, 2x minus 1, minus, this is the operation, and you must open parentheses now before you write in the g function, right, which is x squared plus x minus 2. So now I recommend you distribute the minus. There's an invisible 1 right here. So I suggest you distribute that and remove the parentheses. So I have 2x minus 1 minus x squared minus x and plus 2. And now it becomes like a regular addition problem where we have to combine like terms. So minus x squared, right? This is still unique. So I have 2x minus x, which is plus x or plus 1x, and minus 2, I'm sorry, minus 1 plus 2, which is positive 1. So this is the subtraction. Now let's do the multiplication. Fg of x. So write the f function first in parentheses, and you write the second function also in parentheses, plus 2. I'm sorry, minus 2. Just erase this real quick. X squared plus x minus 2. And now I have to FOIL these things. I have to multiply each term. So the 2x is going to multiply every single term of x squared, x, and minus 2. So I have 2x squared, 2x times x, I'm sorry, 2x cubed, right? 2x times x squared, 2x cubed, 2x times x, 2x squared, and then 2x times minus 2, minus 4x. And now I have to do the minus 1 times everything. So minus 1 times x squared minus x squared, minus 1 times x, minus 1 times minus 2 is positive 2. And now at this point, it becomes just as an addition problem where we have to combine like terms. So the 2x cubed is unique. The 2x squared and the minus x squared are like terms, so I get positive x squared. The minus 4x and the minus x are like terms, so I have minus 5x. And the positive 2. All right? So this is the product of the two. Now, let's do the division. Sometimes, most of the time, the division is the easiest one. F over G. F first, numerator, over x squared plus x minus 2. And there's really nothing that we can do here to divide, so this is in the final form. Now, for example, let's say that my f was 4x squared and my g was 2x. Okay, and then I want to do division. F over g, f as my numerator, g as my denominator. Now, different from this, that I cannot divide anything, in this case, I can simplify, and then I should, right? So I can simplify everything by 2, and the x squared and the x simplify, and I left with 2x. So f over g of x is just 2x. So in this case, I was able to simplify the two functions, but in this case, I was not. So sometimes we'll be able to simplify, in other times we will not. So whenever we can simplify, we should. All right, so this is the basic example when you have two comparable functions. Some simplification is possible, like you've seen it in the addition and subtraction. But in the next case, I'm going to show you not quite possible because functions are not really relatable. Okay, so for example, here is one function, f of x, which is a radical function, and one function, which is a regular linear polynomial function. We're going to find all the four combinations. So it may seem hard because this is a radical function and this is not, but this is actually a lot easier. So f plus g, look how easy it is. F first, g after, and notice they have absolutely nothing in common. So what do we do? Well, we just write them as they are. And we're done. This is the addition of the two functions. The same thing goes for subtraction. They have absolutely nothing in common. So f minus, be very careful here, right? You need to put parentheses here because the minus is being applied to all terms of the g function. So radical x plus 3 minus 5x minus 2, right? There's an invisible 1 that multiplies the 5 and multiplies the positive 2. And this is it. I can't combine them. There are no like terms here for me to combine. Product. F parentheses G. Okay, so now I have to multiply this whole thing times 5x and times the 2. So normally we leave the radical, we write the radical last to avoid confusion. So radical x plus 3 times 5x, I'm going to write 5x radical x plus 3. Now, do not multiply the 5x times the x and the 3 inside of the radical. The 5x multiplies the invisible one that is outside. Okay? Plus, same thing with the 2. The 2 does not multiply x and 3. It multiplies this invisible one that is outside. So this is 2 radical x plus 3. And that's it. That's all I can do. Same thing with division. F over g. Division in many ways is probably even easier. So I have F, and then I have G. Nothing I can do. I have to stop right here. Right? This is the end of my division problem. Now, if they wanted to know the domain of this function, right? So we have two issues here. Normally, we don't need to worry about the domain. I'm not going to ask domain questions on these functions on any exam, but the domain of this function, so we have two situations that the numerator has to be greater than or equal to 0. So this is something that you've all seen in Math 119. So minus 3 on both sides to solve this thing. So this is for the numerator. So the value has to be greater than or equal -3. Otherwise, we don't have a way to take the radical. For the denominator, we have another issue. The denominator, we don't want it to be 0. So the 5x plus 2 cannot be 0. So now I have to solve this equation. So minus 2 on both sides. I have 5x equals -2, and then we divide everything by 5. Okay, so I have the x cannot be -2 over 5. All right, so the domains are real numbers, not these, has to be any value greater than -3. So if we were to write this in interval notation, so first we take a look at this one. So greater than or equal -3. So because of the equal, I use bracket, -3, all the way to infinity. But I have to remove this value. This cannot be. So we go from -3 to -2 over 5. And then from -2 over 5 all the way to infinity. So this is the domain. The issue really, normally it's going to happen in the division, but depending on what kind of function you have, you may have an issue with the multiplication, or just like the addition and subtraction. All of these two cases, we have to make sure that the x value is greater than or equal to -3. But in this section, we are not going to be talking about domain. We're not interested in doing domain for these functions. You don't have to worry about that. All that we need to know is to be able to find all of these combinations of functions: the addition, subtraction, multiplication, and division.